and welcome back to Allen High School's discussion of chemistry at the APIB HL1 level. We're moving into a discussion of changes in the vapor pressure when we mix two liquids. So Raoults came up with a law, and this law is for ideal solutions. Now, in an ideal solution, it is assumed that, so if it was ideal, it's assumed that the intermolecular forces are the same when they are pure, and, that's a U, sorry, and when they are a mixture. So that's what an ideal solution would be. Now, what we want to do is explore that. What Raoults' law says is that the total partial pressure above the liquid is going to be equal to the mole fraction. So if you recall, mole fraction is moles of the part over the total moles. Now we don't multiply by 100 because we're talking about a fraction, which is a part out of 1. And then that would be times the partial pressure of pure A. So that little knot there means of pure A, the partial pressure of pure A, plus the mole fraction of B times the partial pressure of pure B. Now, if these intermolecular forces were roughly the same, all right, so that shows the partial pressure of A, this shows B, this shows their mole fractions changing, right? So as we're increasing the partial pressure of A, it makes sense that, or excuse me, the mole fraction of A, that we'd get more partial pressure. Now, if we take any point, if we add that partial pressure plus that partial pressure, we would get what represents, in this case, the mixture. So this is representing the partial pressure of the mixture as the mole fractions are varied. So if it's ideal, it's a simple additivity of the partial pressures relative to their mole fraction. So you can think of it as a weighted average based on their mole fractions. All right. Now, if it's not an ideal solution, we can see two things occur. One, we can have a higher vapor pressure than expected, and that's because the solution has weaker intermolecular forces. If you increase the strength of the intermolecular forces, you're going to increase the drive to stay as a liquid in the liquid state. Okay? So in this case, we've got a higher vapor pressure. So as we increase that vapor pressure, that means that we have more gas, which the converse of that means less liquid, which means weaker intermolecular forces. Now, a negative deviation, that's a lower partial pressure, would mean just the opposite. As we decreased the partial pressure of the vapor of the mixture, all right, that means we have less gas because it's the gas that causes the pressure. That means more liquid. And so in this case, we see an increase in the intermolecular forces relative to the pure substances. So let's take a look at an example of this. Now, these numbers were chosen so that you could get a nice rough estimate based on these molar masses. So I want to get the mole fraction of acetone. And so that means I need the moles of acetone. Moles of acetone, you take mass over molar mass, and we're going to get 0.100 for our acetone. To get our moles of chloroform, same thing. We take our mass over our molar mass, and it's very close to 0.100. So that means my mole fraction of the acetone is going to equal the mole fraction of the chloroform, and they're both equal to 0.100 over the sum. Okay, so that gives us our mole fractions. Now, Raoults' law says that if it's an ideal solution, that the vapor pressure of the solution should be the mole fraction. If you couldn't do that math in your head, that's 0.5. Should be the mole fraction times the partial pressure. For acetone, it's 345 plus 0.5 times the partial pressure of chloroform, which is 293. And you know me and my silly calculator mess ups. Double check my number, but I'm getting 319 torr. Okay? Now, what the problem says is if you read it, it gives us the vapor pressure of the solution. So our true vapor pressure was less than our predicted. So this is what would be predicted if it was ideal. And since we have less, we have that negative deviation, we must have more intermolecular forces in our mixture than we anticipated. So let's take a look at their structures, because structure determines function, and you've got to be able to link these. So acetone is the same as propanone. You would be given this structure. You don't have to know organic structures, just how to apply. Okay, so that's acetone. Now, do you notice with acetone, it is a polar molecule, and we have a partial negative charge right there. Now, I want to get rid of this here so I can draw what that's going to look like when I see its attraction to chloroform. With chloroform, what we have is we have a C and an H and chlorines. That would be a tetrahedral structure. If you had to do the whole Lewis dot, you need to show all of those dots. It depends on the context of the question. What we're after here in this little explanation is that this is also polar and that hydrogen is partially positive. And that's because the permanent dipole moment is going to go towards those chlorines, the end with the chlorines. All right? And now, anytime we have a positive and negative, whether it's partial or full, we have a chance for a Coulombic attraction, Coulomb's attraction there. So what I'm trying to represent in the green there, often it's a dotted line, I wanted to try to make it clear, is we have a strong dipole-dipole attraction. And that could explain why our calculated 319 would have been ideal. We see that it's actually 260 torr. That's the experimental, which means that there's more intermolecular forces. And those intermolecular forces can be seen right there. Okay, we'll be discussing this way more. Until then, this is signing off.